So I think we have two back-to-back lectures today and tomorrow this week. So today we'll complete the moment of inertia and applications type of concept. So tomorrow we can begin with torque and its applications. So in general, we have understood moment of inertia for a rigid body is integration r squared dm. And we have seen the various formulae, like we have seen for moment of inertia of thin rod, okay, then ring, disc, hollow spherical shell, and solid sphere. So these are some of the standard formulae you have to keep in mind. Okay. And then further we had seen that there are two particular theorems, one of which we discussed last time. So the first one was what we call the parallel axis theorem. Now we'll start with the discussion of the second theorem today, and then we'll come back to the derivation of both of these, parallel and perpendicular axis theorem. So all this we've done in the last lecture, so we don't write down again. So let's start from this point, perpendicular axis theorem. Now this is a bit more specific than the parallel axis theorem. Perpendicular axis theorem is applied to, or it is applicable for laminar surfaces only. That means the mass should be distributed on a plane, or what we call a two-dimensional surface. Okay. Example, a thin disc or rectangular plate or triangular lamina. These kind of situations. Okay. So let's understand the statement of parallel axis, perpendicular axis theorem. So the statement of the theorem is like this, that if we consider a laminar surface of any arbitrary shape, which is lying in, let's say, the xy plane, this is our x-axis, this is our y-axis. The origin need not be the center of mass. It can be anywhere, as long as the two-dimensional planar body we are talking about is lying in the xy plane. So for a planar or laminar body lying in the xy plane, we have the formula that moment of inertia about the z-axis is equal to the sum of moment of inertia about y and y and x-axis. So here it's clearly understood that Iz is moment of inertia about z-axis, which is perpendicular to the plane of the lamina. Okay. And Ix and Iy are about x and y axis, which are in the plane of the lamina. So just write down the statement of perpendicular axis theorem first. Then we'll understand the applications with some examples. And then we'll go back to the derivation of both these theorems, parallel and perpendicular axis theorem. So just start with this. Okay, so let's see some examples of application. So we have the case of a thin uniform ring, let's say. And let's say we take the x and y axis as mutually perpendicular diameters for it. So even though it's not exactly a surface in that sense, but it is still laminar because it's lying in a plane. Okay. So if this radius is r, so this is a thin uniform ring, mass m, radius r, okay, in the xy plane with the center at the origin. Okay. Now, according to perpendicular axis theorem, Iz should be equal to Ix plus Iy. This is statement of perpendicular axis theorem. And Iz will be equal to mr square. Because you can see, yes.
The laminar surface means on in 2D plane. No?
Yes. So all the mass should be lying in a plane. So that's happening in the case of a thin ring, right?
Yes.
It's a thin ring is in a two-dimensional plane. No? So we can apply perpendicular axis theorem to it. Okay? So Iz will be mr square because the z-axis is the symmetry axis. So the z-axis is in fact the symmetry axis. So moment of inertia about z-axis is integration r squared dm, which is this derivation we had done last time, right?
Yes, sir.
So like, think of it like this. This is your ring. This is your z-axis. So all the mass is equidistant from it. Any mass dm on it is like this. So it's mr square. Okay. And also you can see Ix will be equal to Iy. This is by symmetry because both x and y axis are diameters. Okay. So the same distribution of mass with respect to them. So now if you put together this statement, okay, along with this statement, in the statement of perpendicular axis theorem, so you get that mr square will be equal to 2 times Ix or 2 times Iy. So moment of inertia about x or y axis should become mr square by 2. Something we had also done by integration earlier. Let's see. So this result is also shown by integration. But now this is an easier way to demonstrate this and demonstrate perpendicular axis theorem by this. Okay. So just make a quick note of this example. Then we'll move on to more applications and examples. So this was a familiar known result, but you can see how we have used perpendicular axis theorem to verify it. But of course, the key to this situation was not only the statement of perpendicular axis theorem, but the symmetry also. If this had not been symmetrical like this, then we could not have written this as 2 times Ix or 2 times Iy. Okay, so this example is clear, I hope.
Sir, one.
So 1 minute.
Done.
Okay, done. So let's move on to interesting example we can solve using this. So now instead of a ring, let's say we have a thin disk. And we want to calculate the moment of inertia about some particular axis, which I'll tell you about. So this is a thin disk of mass m and radius r. So three-dimensionally, it's looks something like this. Its thickness is negligible. So once again, let's say that its center is at the origin and it's lying in the xy plane. So in this diagram, the z-axis will be the symmetry axis, cutting it like this. This will be the z-axis. So these are the x and y axis, let's say. So we want to find the moment of inertia about, first of all, a diameter axis. That is an axis passing through the center and in the plane. And we also want to find out the moment of inertia about an axis tangent to the disk. So this second part means something like this, that if this is our disk, in a three-dimensional diagram, this is our disk. Now imagine the axis is like this. The disk is rotating like this about this axis. It's tangential to it at a certain point. You want to find the moment of inertia about this.
Sir, that it is in the plane or not? That axis.
Yeah, obviously, no? Tangential will be in the plane, right? So what is the definition of tangent at a point? It is at any point on the circumference, it is a line which is perpendicular to the radius in its plane, no?
Yes.
Right? The mass of the disk is m and radius is r. Let's try this out. We'll discuss. Yes, very good, Jay. That's correct. Okay. So far, one person has sent the answer, but that answer is correct. Very good. So for the first one, it's exactly the same concept that you can use. for the ring that we had seen. Only the value will become different for Iz. Okay, so this is your perpendicular axis theorem. And Iz is mr square by 2. This is the standard formula that we know from integration. So this is, as I told, you have to remember the standard formula that we had listed out last time. Okay. Otherwise, this will become a very lengthy problem. You have to first do the integration to establish this. We don't want that. Okay, so because z-axis is the symmetry axis. Now, once again, Ix is equal to Iy, because both are diameters. They are symmetrical. So you can see that Ix will be equal to Iy, will be half of Iz, which become mr square by 4. So any diameter axis moment of inertia will be like this for a disk. Okay. Now when it comes to the second part,
So we can use parallel axis here.
correct. Okay. So Jay, that is the method you used. Parallel axis theorem, right? Okay. So what we can do here is we can just consider
So it will be parallel to diameter, no?
Parallel to the diameter. The diameter is passing through the center. Let's say I've arbitrarily taken this point as my P. I want to calculate moment of inertia about this axis. So I just choose another axis which is parallel to this one, but passing through the center of mass. So that becomes nothing but a diameter axis. Okay. And the perpendicular distance between these two is R. So ICM in this case is mr square by 4 because it's a diameter axis. So IP just becomes ICM plus MD square. This is our statement of perpendicular axis theorem. And here D is nothing but R. So my moment of inertia about that point P that becomes 5 by 4 mr square. So this is the moment of inertia about a tangent axis for the disk. So notice there's a lot more than this because the mass distribution is such that it's much further away. So for this, you can see the radius of gyration. Remember, we discussed about that last time, is r by 2. For this, the radius of gyration is root 5 by 2. So this radius of gyration is a lot more compared to this because the same amount of mass with respect to the tangent, it's distributed much further away from the tangent compared to with respect to the diameter.
Sir, there will be parallel, no?
Yeah. This tangent and this diameter are parallel to each other. So, oh, sorry, it's parallel axis. Correct. This one you are saying.
Yes, sir.
Yeah, this is parallel axis. Correct. Okay. So this is like one of the standard types of applications you should remember of these theorems. You can apply it to, for example, ring and disk and situations like this. Okay. Now another set of standard applications for these theorems is how we develop the formula for moment of inertia for a rectangular plate. Or a rectangular thin lamina kind of thing. About various different axes, we'll develop the formula. Okay. So let's say this is the top view of a rectangular plate. So in 3 dimensions, it's more like this. It's a thin plate, so this thickness is negligible. Let's say the dimensions are L on this side and B on this side. Okay. Now, if I consider the plate to lie in the XY plane such that the x-axis bisects the width and the y-axis bisects the length. And naturally, O is the center of mass. So this is in the XY plane, with O as the center of mass, and X and Y axis bisect the rectangle. And it has mass M, dimensions obviously L into B as we've seen. This is L, this is B. Okay. So in this diagram, you can see that this would be my y-axis, which is bisecting the length, and this would be my x-axis, which is bisecting the width. Okay. And more importantly, z-axis would now be like this one. It's perpendicular to the plane passing through the center of mass. So z-axis is through the center of mass at O and perpendicular to its plane. So let's start with calculation of moment of inertia about all these axes. I will find out Ix, Iy, and Iz. So let's start with Ix. So for Ix, we will go back to a standard formula that we know. I'll bring back to this diagram. And that is the moment of inertia of a thin rod. So I want to calculate the moment of inertia of this rectangular plate, but about this axis, which is basically bisecting its width B like this. So this is my x-axis. Here's my origin. So what I can do here is I can slice this into thin rods like this. Anyhow, so say I take a thin section of this, which is at a position, let's say x with respect to the origin. But more importantly, it has a thickness dx. Right? And what will happen is this will have a width. I mean, this rod will have a length of b because this length is b, whereas this length is l. Okay. So this differential, this section, you can say, it's like a thin rod. Okay. So it has a length of b and thickness of dx. So it has an area of width or length into thickness. Okay, so it has a mass dm of sigma into dA. So sigma is total mass upon total area. So this thin rod, it has a mass dm of, ultimately we'll see m by b, sorry, m by l into dx. Okay. Now, what kind of axis the x-axis is for it? It's the perpendicular bisector. So this thin rod, this differential thin rod's moment of inertia about the x-axis. What will that be? That will be dm into b square by 12. Okay. Please understand why it's dm into b square by 12, because if I have a rod like this, whose length is, let's say, capital M and mass is m, and I consider the axis passing through its center and bisecting it perpendicularly, moment of inertia by integration we had seen was ml square by 12. So here that L is small b actually, because this rod is of length b, and the x-axis is the symmetry axis for it. It's a perpendicular bisector for it. So that's the moment of inertia of that small section. So moment of inertia of the entire plate, for the rectangular plate. So this will come by integrating these, all the rods. Okay. So now you notice that we did not even substitute dm, because b square by 12 is common for all that. However, we can do that. Okay, so we'll write this as m by 12l into b squared dx. Now this x has to be integrated from minus l by 2 to l by 2. Or we can just bring all this outside and see we are left with integration of dx from one end of the rod to the other end of the rod. So that will finally give us mb square by 12. So that is the answer to the first part. Moment of inertia of this rectangular plate about this x-axis, which bisects the side D, that is mb square by 12. Okay. So now you'll also realize when you go through this and note this down, how you will calculate moment of inertia about y-axis. You'll take horizontal strips instead of vertical strips, okay, and apply the same principle. So your answer will come very symmetrical to this. It will come ml square by 12. Okay. So yeah, things will get too small. So let's. Okay, so just take down the heading and this thing first, then we'll come back to the working for moment of inertia about the x-axis. Okay, so let's scroll
Sir,
down to
can
this
you
now.
wait?
7 minutes.
Yeah, finish with the top part.
Yes, sir. Top one. IX.
You have to write.
Sir,
Yes, sir, that
IX.
party.
Okay, finish this.
Sir,
Yes.
sir, could you scroll down?
Yeah. Okay, so now as you're noting this part down, you can also immediately work out yourself how you will find IY. Okay. So same kind of method you'll use, but taking horizontal strips which are symmetrical about the y-axis, which bisects the length L.
Means in its length will be L, na?
Yes, it will become ml square by 12. Okay, so hope all of you would have understood that you will get Iy by a similar process as ml square by 12, right? And then you can go on to use perpendicular axis theorem. So for Iy, you will have to, because this is your y-axis passing through the center and bisecting this length. So you will take thin horizontal strips like this. Thickness dy. So you will see that this time your dm will be, should be m by b into dy. So when you integrate this, you end up integrating this. So now putting all this together, you can understand that the moment of inertia about the z-axis can now be calculated by using parallel axis theorem, sorry, perpendicular axis theorem. So you get this. Okay, so this is about the axis through the center of mass and perpendicular to the plane of the rectangular lamina. This is a perpendicular axis theorem.
Sir,
Yes.
sir, that L square by 12, how that came?
Which one?
Sir, in IY.
Yeah, so it came from this integration. Beta, see here. This you understood, na? The thin rod of mass dm, its length is L, na? And the y-axis is bisecting it. So it's dm into L square by 12. Understood now?
Okay, R square. Yes,
Now you
sir,
replace dm with this term like this over here, right? And integrate for all the rods from the lowest one to the highest one. So your y coordinate is going from minus L by 2 here to plus L by 2 here. Oh, sorry, minus b by 2 to plus b by 2. So completing this integration, you will get this. So all these terms come out now. ml square by 12b. Right, left with integration of dy from minus b by 2 to b by 2. So finally, that will give you this step. So exactly the same kind of steps as the previous one. Only the geometry is like perpendicular to that one in the diagram. Now we can also use these results for some more examples of applications. So for that same rectangular plate, for example, we want to find the moment of inertia about either of the edges, then we can do this. Okay. We can use parallel axis theorem. So for example, now if we take this as our axis, this axis like this, then we can compare this with the parallel axis passing through the center. And if this is L by B and the mass is M, so here I can see that about this axis to the point P, this perpendicular distance is L by 2. So by using the fact that IP is equal to ICM plus MD square, so the moment of inertia about this edge will become the moment of inertia about this axis, which was ML square by 12. Just now we had seen this was our IY earlier, plus M into now this D is L by 2 square. You can see moment of inertia about this is ml squared by 3. Or another way to understand the same thing is also by integration. What we can also do is, instead of using the theorem, if we are considering this as our axis, then we can just cut a thin strip like this. That strip is of length L and mass dm. So its moment of inertia about this axis will be dm L square by 3, using the formula for the rod about the perpendicular axis through its end. So this will come from integration of this. If you do this integration, you can again show ml square by 3. Similarly, if you consider the other edge, that is the edge which coincides with one of the lengths. So you can see you'll get similar kind of formula. So about this axis, we can consider parallel axis through the center. So this one, or let's say this is Q. So this moment of inertia about Q will come to be mb square by 12 plus m into b by 2 whole square. This is b by 2. Moment of inertia about this axis is here. This. So using this, we can see that moment of inertia about this other edge is mb square by 3. And now using this, we can also find moment of inertia about this corner axis, which is perpendicular. An axis passing through a corner and perpendicular to the plane. We can combine these two in perpendicular axis theorem and find that out. Okay. So this way we can find out sort of any arbitrary axis or any of the logical axis with respect to the rectangular plate. We can find out moment of inertia in this way.
Sir,
Yes.
sir, I'm not understanding that how L square by 3 came in that integration part.
This, I have
Yes.
not done it by the integration method, but this I told you to do for, you can check this out later as a homework problem. Here you understood na, application of parallel axis theorem.
Yes, sir, that I know.
So just note it down by this method.
Sir, but I was asking.
This is clear na, this one how the calculation has come.
Yes, sir, that.
Yeah. Okay, so finally from this we can also see that
You're done.
okay, so let's come to the final part of this set of derivations. So now if we consider an axis passing through the corner of a rectangular plate and perpendicular to its plane. So we can do that by once again applying perpendicular axis theorem, but this time we should take the x and y axis as the edges instead of the perpendicular bisectors. So we consider this to be, for example, our y-axis. This to be, for example, our x-axis. Then to find out moment of inertia about this axis, passing through the corner and perpendicular to the plane. So here the z-axis is the axis to one of the corners and perpendicular to the plane of the rectangle. So we can calculate Iz as the sum of Ix plus Iy, because obviously these are all mutually perpendicular axes. Right? Now Ix over here will become mb square by 3 because it's this edge. Iy will become ml square by 3. So Iz will become m by 3 into L square plus B square. Or we can also show this by another method that earlier we had seen the moment of inertia about an axis passing through the center and perpendicular to the plane. So this axis we had seen. It was m by 12 into L square plus B square. So now we are considering this axis passing through this corner, which is P, and the perpendicular distance is half the diagonal. So IP will become ICM plus MD square, where D is this, half the diagonal. So if you apply this also, you'll get the same. So there are two different methods by which you can find this out. Now let's look at the proofs of these two theorems.
Sir, could you just go up for a moment?
Okay, but write down fast.
Done, sir.
Done? Okay. Good. Yeah, so let's look at the proofs of these two theorems very quickly. So starting with the parallel axis theorem. So remember, parallel axis theorem applies to any three-dimensional kind of rigid body. It's not restricted to two-dimensional. So let's imagine that this is the center of mass, and the axis that I've considered through the center of mass, I'm taking that as my z-axis. Okay. This is the y-axis and this is the x-axis. And deliberately, I'm considering the x-axis along, that perpendicular distance between the 2 points P and C. So when I consider some axis through the point P, I'm considering the x-axis as the line joining that point with this center, such that these two axes are parallel to each other. So now when we are considering moment of inertia about the center of mass axis, now just so you have to understand, this is a three-dimensional diagram. Okay? So if I take the top view of this diagram, that is, I'm viewing this from the top, it looks something like this. This is my x-axis. This is where my origin is. So the z-axis is coming out of here. So the center of mass is lying on this axis. Okay? And this is where the point P is on the x-axis. So it's located at d, 0, 0 in comparison. And the mass is distributed over some kind of situation like this. Okay. So now consider any arbitrary particle within the rigid body of mass dm, which is located at a point x, y, z. Okay. So that point in this diagram will look like this, though it actually might be outside the plane of. Okay. So this dm is located at x, y, z. So what is the perpendicular distance of this dm from this z-axis? This is the perpendicular distance, let's say r. So r is equal to square root of x square plus y square, where r is the perpendicular distance of the particle dm from the z-axis, which is, by the way, the axis through the cm. Because the center of mass is where my origin is. So moment of inertia about the center of mass axis will just become integration of r square dm. So that is integration of x square plus y square dm. So this is my first equation. Okay. Now consider the same particle with respect to this axis now, the one passing through the point P. So that particle's distance, perpendicular distance from this axis is this one. Let's say that is r prime. So now r prime is the perpendicular distance of the particle dm from the axis through the point P and parallel to the center of mass axis. That is basically the z-axis. So r prime will be basically what? R prime will be square root of x minus d whole square plus y square using coordinate geometry. Okay. So the moment of inertia of the system about this axis will be integration r prime square dm. Integration of r prime square dm. So that will become x minus d whole square plus y square integration. Okay, so this is the second part. Now next step, what we'll do is we'll compare these two equations, and by the comparison of these two equations, we'll be able to establish the relation that IP is equal to ICM plus MD square. So we'll come to that step, but first note down this much. We'll have to do some algebra after this for the final part of the proof. So understand that this is a three-dimensional solid rigid body. And C is the center of mass at the origin of our system. So that's how we set up the geometry of the problem. We can take X, Y, Z axis however we please. So we have selected our origin at the center of mass, and we have selected the X-axis such that it lies on the perpendicular from the center of mass to that axis through the point P. So ultimately, the perpendicular distance between these two axes, that is only D. Okay. This distance over here, this is D. Okay, so now let's compare these two. So if you just expand this IP a little bit here, so you can see it is x square plus y square minus, or let's write it plus d square minus 2xt into dm. Okay, so you can separate it out like this, that it's square root of, I mean it's integration of x square plus y square dm, okay. Then integration of d square into dm, and then minus 2 times integration of xd into d. So this quantity you can see over here is the same as ICM. So you just replace this whole integration with ICM. In this quantity, d is a constant, and in this quantity again, I'm left with this. Now here you can see this integration here, integration x dm to n, because that was definition of position of center of mass. Recall. So x coordinate of center of mass was integration x dm divided by total mass. Okay. Now here the x coordinate of the center of mass is 0, because the center of mass is at our origin. We have selected our origin in that way. Okay. So that's why this term will come out to be 0. Whereas this term, d is outside, so you integrate it totally, so it's d square into total mass. So this is a simple proof that the moment of inertia through this other axis, which is parallel to the center of mass axis, is given by the formula. Okay, people, so hope this proof is clear. Now moving on to the perpendicular axis theorem. It's actually a much simpler proof. So here, remember, we are talking about a laminar body. It's not a three-dimensional. So imagine our lamina is lying in the XY plane like this. The Z-axis is cutting it perpendicularly. So the top view of this will look like this. So now consider any particle dm. Now it's lying in the xy plane, so its coordinates will be x, y, 0. So this is a lamina in the xy plane. So for this particle lying over here, the perpendicular distance from the x-axis is nothing but its y coordinate. The perpendicular distance from the y-axis is nothing but its x coordinate. And the perpendicular distance from the z-axis is nothing but square root of x square plus y square. That is the perpendicular distance from z-axis, whereas x is the perpendicular distance from y-axis, and y is the perpendicular distance from x-axis. For particle dm located at a general coordinate like this. Okay, so our moment of inertia about the x-axis becomes integration y squared dm. Our moment of inertia about the y-axis becomes integration x squared dm, and our moment of inertia about the z-axis becomes integration r squared dm, which becomes this. Okay, so you can see that separate these out. So this is nothing but our Iy, and this is nothing but our Ix. So this condition will always be satisfied as long as the body is planar and it's lying in the xy plane, and z-axis is therefore cutting it perpendicular. Okay, so these are our two theorem proofs. Now,
Sir, one
just to
minute.
wind up moment, yeah.
Sir, proofs will be not asked, no?
Sorry,
Sir, proofs will be not asked, no?
not in general, but this, see, the thing is in HSC, if you are in a HSC junior college, then part of part of rotational dynamics is in class 12th and part of it is in 11th. So the part which is in class 12th will be tested in your board exams, right? And then the proofs can become important.
Sir, 1 minute, can you show?
Not finished? Okay.
Done, sir, done.
Oh. Now, a couple of more examples about moment of inertia, and then we'll be done with this. So, for example, very important moment of inertia of a solid cylinder about its symmetry axis. So, this is not something difficult to work out at all. But let's just understand how it comes. So, imagine this is a sort of a side view or a three-dimensional view. Of a solid cylinder. So this is the symmetry axis, the one that passes through its center and is parallel to its length. We want to find the moment of inertia about this axis. So the radius of the cylinder is r, and this length is L, and its total mass is m. So the front view of this will look like this. If you see it from front on, you will just see it like a disc, because you'll just see the cross section. And the particular axis we are talking about is this one. This radius is r. Okay. Whereas if you see the top view, it will just look like a what you would understand is this is actually the curved surface like this, or cross section like this. This is the axis of rotation. So now to understand the moment of inertia about this axis, what we do is we just slice it into discs. So if we consider a thin disc like this, now you'll see that we don't even need to take the thickness of the disc and all that, because all the discs are having the same kind of situation. So we consider a thin disc. of mass dm. Okay. But its radius is also r. So that thin disk will look like this over here. Some thickness like this. Okay. So the moment of inertia of this thin disk about that given axis will be how much? It will be dm r square by 2, because it's the symmetry axis for that disk, right? So now the moment of inertia of the cylinder, we have to integrate the moment of inertia of all disks. Okay. So that is integration dm r square by 2. But luckily for us, what happens, capital R is a constant. So we don't have to substitute dm in terms of dl and all that. You can see it's nothing but mr square by 2. So interestingly, it's independent of the length of the cylinder. It only depends on the mass and radius. So this is moment of inertia of a solid cylinder about its symmetry axis.
Sir,
Yes,
so what you said about the independency of that?
it's independent of the length. No? See, it does not depend on the length. It depends on radius and mass only.
Okay, sir, got it.
That means we have first only find that moment of inertia of disk.
Yeah, basically you slice it into disks, and we already know the formula of moment of inertia of a disk. So this is coming from that derivation we've done earlier. Moment of inertia of a disk about its axis. So the disk's mass is m, it's mr square by 2. Here it's a differential disk, its mass is dm.
Sir, then its limits will be what? When we will
That's the thing.
integrate?
I said you don't need to substitute limits and all that, because r square by 2 is coming outside the integration. So integration of dm is nothing but total mass. No?
Oh, yes, yes. Done.
Okay. So now similarly, the final example of moment of inertia, if we have a hollow cylindrical shell, okay, mass m, radius l, radius r and length l. Okay. So moment of inertia about the symmetry axis. So it's very similar, but the difference is this time when we slice the hollow cylinder, instead of discs, we'll get rings. Okay, so that's the only difference. So this is not solid from inside, it's hollow. It's got a thin crust, so it's not very thick. Yes. So this, now again we are considering this symmetry axis. So this time when we slice it like
Then it
this,
will be ring, no?
yeah, we'll get a ring. So this would be a thin ring of mass dm, let's say. So if this one's radius is r, then the ring's radius is also r, and is the same symmetry axis. So the moment of inertia for the thin ring about the symmetry axis will be dm r square. So moment of inertia of the cylindrical shell will become so mr square. So hollow cylindrical shell has the same formula as ring, and solid cylinder has the same formula as disk, because the distribution of mass with respect to the axis is the same. Okay, so with this, we complete the portion based on moment of inertia. Okay. We have a lecture tomorrow, so we will continue ahead with the next part of rotational mechanics, which is dynamics of pure rotation, that is the relation between torque and angular acceleration. So we'll start with the definition of torque, and we'll see how we express the equivalent of F is equal to ma in terms of torque for a body rotating about a fixed axis. So very important section of rotational mechanics tomorrow.
Thank you, sir. Bye.
Okay, people, that's it for today's session. Thanks for attending. Wish you all the best.
Thank you, sir. Bye, sir.